Okay, I believe we're ready to start. Hello and welcome to this webinar on the International Energy Agency 22 megawatt offshore reference wind turbine. Today, my name is Fredrik Zahle from Technical University of Denmark, and today I have Pietro Bortolotti and Daniel Salkind from NREL together with me, as well as Will Collier from DNV. We have a 1-hour session here where we will go over the turbine. And here you see an outline of what we'll be talking about. I will start out with a brief background and overview of the turbine, followed by some details on the rotor design. And then I'll hand over the mic to Pietro that will describe the drivetrain tower and monopile design. Dan will talk about the floating platform design, and then in place of Thanasis Barlas, I will also give an overview of the aeroelastic stability and design loads, characterization of the turbine, and finally will give an overview of a code-to-code comparison that was recently published on this IEA 22 megawatt turbine. That part is 30 minutes, and then we should hopefully also have 30 minutes for a Q&A, and I'd like to point you to the Q&A tab in the Zoom meeting, where you will be able to post questions that we will, to the extent possible, try to answer. This session is being recorded and will, following this, also be published online for people to watch or rewatch. So let's dive into it with a bit of background. Many of you will know that there are several reference wind turbines available that have been developed over the last many decades, primarily driven by the need in the research community to have common reference systems, some ranging from purely aerodynamic definitions of wind turbines, but also others more and more sophisticated with a full turbine definition. Some of these are released through the IEA Wind Task 37 and now 55. And these reference turbines form a very important basis for several research projects where it can be very challenging to work with commercially available products. But in fact, the industry also has many uses of reference wind turbines. This could be all the way from OEMs, operators, and subcomponent designers that both need representative reference systems for current technology, but certainly also for future technology. And in light of both continued innovation on turbine design and manufacturing, but also upscaling, we found that there was a need to release new reference turbines, and that's the one of the contexts of why we have this IEA Wind Task 55 to release continuously new reference systems, both turbines and wind plants. One of the first steps in Task 55, which was also initiated in Task 37, was the release of this IEA 22 megawatt reference turbine that we will be describing today. This is an entirely fictive turbine, and it is not necessarily stating that we are certain that 22 megawatt turbines will be in the market, but it will allow us as researchers and industry to evaluate the feasibility of these large machines with a representative design of a possible how a 22 megawatt could possibly look. I also want to stress that this is a conceptual design. This is not a fully detailed design to the level of what you would see from a real turbine, but sufficiently detailed and designed to a level where it can represent this future technology. The IEA 22 megawatt was initiated in a collaboration between NREL and DTU. On both sides, we had been initiating developments of turbines and systems in this size, which led to us to work together to jointly design this 22 megawatt turbine, initiated, as I stated, in task 37 and now finalized in task 55. At DTU, we led the overall coordination of the design process and led the rotor design, along with extensive load validation and stability analysis of both the bottom fixed and floating platforms. NREL designed the rest of the turbine, drivetrain, tower, monopile, and floater. And of course, we iterated back and forth on the validation of this design. Then we have also worked closely with collaborators from DNV and TU Berlin, where we conducted a code-to-code verification between 4 commonly used Aeroelastic codes. And this has really been instrumental to developing the turbine to the level that it is now. And we'll also see some overview of those results today. So what we will present today is a very short overview of what is in the technical report. You can find the technical report published with the title that you see here, and where you can dive into all of the details. Of course, I also want to acknowledge the co-authors of this that are not necessarily presenting today, but have been a very key input, provided key input and work into this. Thanasis Balas, Kenneth Lundbeck, Lu Wang, Kasper Labouchange, and Lassas Sethuraman, and Garrett Bata. So a high-level overview where it could make sense to look at, well, how does the 15 megawatt that was released some years back compare to this new 22 megawatt? We have, of course, increased the rotor diameter, but actually also increased slightly the specific power of the turbine. The 15 megawatt had a specific power of 326, and now we're a bit higher at 347. Another notable difference is also that the tip speed has been increased considerably to 105 meters per second compared to 95 meters per second for the previous turbine. When we look at the overall component masses, we will also see, of course, an increase, and some of these are directly comparable and others less so. For example, for the blades, we have also used a different moduli composites, which allows us to reduce the mass of the 22, relatively speaking, to the 15, and so forth. For the other components, there will also be some specific, you could say, differences that may not make them directly comparable. So the rotor design has been done using DTU's in-house framework, ASOPT, where we conduct a fully coupled optimization where we simultaneously design the aerodynamic planform, internal structure, and steady state operating schedule, where we seek to maximize annual energy production, subject to a variety of different constraints. On the right here, you then see the overall workflow that is being run in that optimization tool, where, as I said, things are being sized simultaneously using numerical optimization. The aerodynamic geometry, some parts of that were fixed by choice. Root diameter, maximum chord, and prebend were chosen a priori. We continue using openly available airfoils, although these airfoils were not, you could say, designed for very high Reynolds numbers. They remain fairly well-performing, and we have used these across many of the reference designs available. The polars that we use for the elastic computations were done using DTU's in-house incompressible CFD solver at representative Reynolds numbers, where we conduct both clean and tripped computations that are available in the data set. If we move on to the steady state performance, we can here see the consequence of the design constraints, where we allow the simultaneous design of the pitch ramp with imposed constraints on loads and deflections, where we see that there is a moderate peak shaving introduced into the design that is then also reflected in how the structural design it comes out of the design tool chain. What is also notable is that we have a quite significant amount of torsion in the blade, which means that when predicting rotor performance, you cannot neglect deflection and torsion any longer. You really need to include these in analysis to get the same response as we get in this analysis here. On the structural design side, we are using a cross-sectional finite element tool called BCAS to predict the beam properties. And you can see a representative cross-sectional design or cross-sectional shape of the blade at 20% radius. The blade features carbon-based load-carrying spar caps, 2 main shear webs, and an aft shear web, relatively conventional design. And you also see here references to the materials that were used, developed in a previous project between Sandia and NREL. Also, I want to note here that this design is a conceptual design. We have not conducted 3D finite element analysis on this, which means that there could definitely be areas of the design that do not fulfill constraints you might have from higher fidelity modeling. Moving on to the strength analysis, here we then loop back between the load analysis and the strength analysis, where we apply the loads coming out of a full design load basis or DLCs from DLC 1.2 and 1.3 computed with Hawk2, and then we apply these load vectors to check that the ultimate strength of the blade holds. We have not evaluated fatigue and buckling capacity of the blade yet. Then I turn over the word to Pietro, that will take us through the drivetrain design.
Thank you, Frederick, and welcome all to this webinar. I'm Pietro Bortolotti. I'm a senior researcher at NREL, the National Renewable Energy Lab, and I'm also the operating agent for Task 55. And at NREL, we led the design of the drivetrain, which is very similar in concept, in configuration to the one of the IEA 15. It's a direct drive configuration where the generator has an outer generator rotor with interior permanent magnets and an inner stator. This is maybe the key difference, aside from the sizing, between the IEA 15 and the IEA 22. The IEA 15 generator mounted surface mounted magnets, while this generator at 22 megawatt has interior permanent magnets. And the technical report describes the reason behind this change. We have two set of bearings, upwind and downwind, mounted on the turret. You see in the image on the right, which should not be scaled. And then, like the IEA 15, we have a conical bed plate with a flange connecting to the generator state, transferring the loads from the rotor, the turbine rotor, to the hub, onto the yaw bearings, and then the tower. Okay, so the generator design was performed, I would say, at quite a decent fidelity, better than the IEA 15. The generator of the IEA 15 was a little heavy, was 10-20% heavier than state-of-the-art direct drive generators at 15 megawatt. We believe that we have a better design for the 22, more representative. We started the design in the electromagnetic solver PyFem, which is an open source library solving the electromagnetic equations in mid-fidelity. But then we also performed higher fidelity checks in a combination of Altair, flux and hyperstudy, and ANSYS mechanical, ANSYS workbench, and overall geometrical checks in SolidWorks. We did not start from scratch with this generator. We had a previous study that is described in this DOI, in this journal article, and there is more background there about the design approach. The other components of the drivetrain were designed within the WISDOM, with the Wind Plant Integrated Systems Design and Engineering Model, which is our conceptual design tool that has been developed at NREL for the past 15 years, and specifically within the module Drivetrain SG. Here at the bottom, you see a plot of the efficiency of the generator across the rotor speed. And obviously, if there is the rate at rated, we are at 95.3%. Some of the masses of the whole drivetrain, the hub is down to the hub system, including the pitch system, is at 120 tons. Then the bearings at 55 tons, the generator 508 tons. These are huge components, as you can imagine, and this will actually challenge the technical economic feasibility of this turbine. The total mass of the nacelle, when we exclude the hub and the yaw, is 121 tons. When we include the hub and the yaw, it's 978. And the full rotor nacelle assembly is at 1,200 tons. That was for the drivetrain. And again, the report goes quite in some detail about the design process. You'll see that some components are designed at better fidelity, for example, the generator, than others. Notably, we are lacking a detailed pitch system design or a yaw system design. So there we use some simple scaling laws. We went on designing then the fixed bottom tower and monopile assembly. The turbine has a hub height of 170 meters, and we designed the monopile for a water depth of 34 meters. The monopile goes into the seabed for 45 meters, and the tower starts 15 meters above the mean sea level. The total monopile length is 94 meters. The tower length is 149. We have a transition piece of 100 tons. And overall, if you're wondering about the clearance between blade tip to the mean sea level, is only 30 meters. We designed the tower and monopile again in WISDOM. Now with the modules Tower SE and Fixed Bottom SE, we use the steady state loads coming from the Rotor design. We set a hard max outer diameter of 10 meters for the monopile and the tower. You see on the bottom left the plot showing the outer diameter in red of the monopile and green of the tower. We did receive feedback that today the state of the art is 9 meters, but that it is a little bit of a challenge to design it at 9 meters. Anyway, so the design imagines an improvement of the technology so that we can support 10 meters outer diameters. We designed against, so we had to satisfy constraints on maximum stress and buckling. We set maximum diameter to thickness ratios between 80 and 160. This was a weakness of the tower of the IEA 15. The wall thickness had to be monotonically decreasing just to support the optimizer. And we had a minimum frequency of the whole assembly of 0.15 hertz. And when it comes down to the total masses, the tower mass is almost 1,600 tons, and the monopile is 2,100 tons. We verified with some industry partners that these numbers are fairly representative. Dan, floor is yours.
Intro. Yep. Hey, everybody, I'm Dan Zalkind. I worked on the floater design and the controller design. And so we set out to kind of keep the same architecture as the 15 megawatt, like a Volturnus platform with one main column and 3 outer columns. but we wanted to use this wisdom and wise design environment in order to do design optimization. And so the way it works is we kind of weave our way through this wise stack from the bottom to the top. We start with our wind IO, parameterized turbine and floater. So we take everything that Pietro and Frederick talked about, from the blades to the tower, and put that all into this turbine. Wisdom converts it into something with mass and cost. There's a number of other pre-processing tools that give us our thrust surfaces, our power surfaces, which we then can use to design our controller and also do our modeling. So we used RAFT to do dynamics. This is a lower order model that in the frequency domain gives us steady state pitch angles, maximum offsets for cabling constraints. So we used that to do a design optimization of the platform. And then we used OpenFast to verify those dynamics and also do our controller design. So yeah, on the next slide here is just a kind of a convergence of this design optimization. Our goal was to optimize the draft or the bottom of this floating platform, the column spacing of these outer columns, and also the diameter of these outer columns, with a goal of minimizing our total structural mass. So it's a little bit awkward that our mass actually goes up in this convergence, but the reason why that happens is because we also need to satisfy all the design constraints. So we've got constraints on the metacentric height. We've got constraints on the natural periods. We want to keep those outside of the wave region. Then we also want to keep our maximum platform pitch below 5.5 degrees there. And we also have constraints on standard deviation of pitch or pitch motion and the maximum nacelle acceleration. We try to keep that below 2 meters per second squared. So we kind of took the output of this design optimization, rounded off the numbers to nice kind of round numbers, and in kind of a conservative way. And we've got the values here on the next slide. Not sure if I'm under control yet. Here we go. Cool. So here's kind of a comparison between the 22 megawatt platform and the 15 megawatt platform. You can see the geometries here on the right. And it looks like a nice kind of scaled up version of this 15 megawatt platform. So our draft increases from 20 to 25 meters. We kept that freeboard at 15 meters, but our column spacing was really the main thing that increased here from 51 meters to 65 meters. We got some feedback that this was a really large platform and there aren't a lot of ports that may be able to tow out this platform, but that's what was needed in order to keep these platform, the offsets below the constraints that we needed. It was interesting that the column diameter settled down to the same value, and we kept our pontoons at a kind of standard 10 meters there. We see that our hull mass goes up a little bit, and one change that we made from the 15 to 22 was to get rid of any slurry mass and only use seawater ballast for this turbine. So there's seawater ballast in the outer columns and the lower pontoons. We did that mainly for simplicity, but actually with talking with the UMaine folks that designed the last one, that's something that they kind of do these days as well, because it's free and it's easy to pump in and out. So it's a much more massive platform, but quite a lot of that additional mass is in the ballast there. And then we've got all of our natural periods there on the right, and we tried to keep those outside of the wave region. So we did a pretty good job. We would have liked to get that heave a little bit higher, but that's sort of what it settled down to there. And then we also designed our reference open source controller, or ROSCO, for this 22 megawatt turbine. So we use the peak shaving from Frederick that they have during their rotor design. So that's baked into the controller. And then we optimize the pitch controller. So that gain scheduled PI controller and that floating feedback. And so there's some coupling between those two modules. So it makes sense to kind of optimize those at the same time. Our goal in that optimization is to minimize our tower base damage equivalent loads. We do that over all DLC 1.1 cases, since that's sort of our normal operation. I should have said for the platform design, we did it in DLC 1.6 and 6.1. So these severe sea states are really what's driving the platform design, but we use normal operation to design the controller, assuming that we can kind of detect these off conditions during normal controller operation. So yeah, we've got a paper here where we go into more details of all these optimizations, the controller, the platform, even both at the same time for a control co-design study. So that's a torque paper that we presented last week. So yeah, with that, I'll hand it back over to Frederick.
Thanks very much. So the next step for us after the full turbine was defined was to evaluate the turbine using Aeroelastic tools. On the animation here, you see a ramp-up case for the floating turbine simulated in Hawk 2. This model setup and Aeroelastic evaluations were carried out by Thanasis, who unfortunately couldn't join today, where we included both the monopile and floating platforms. We used stiff bodies and concentrated masses for tower top, connector, shaft, and hub, linear beams for the monopile and tower, and full non-linear or multi-body with Timoshenko linear beams for the blades, where we include this full 6x6 stiffness matrix formulation. There are two controllers at play here. We just saw Dan's tuning of the Roscoe control that was used in OpenFast, but at DTU we are using the DTU Wind energy controller that was then also tuned to these turbines here. Including also for the floating evaluation, we include WAMET and ESIS mooring and hydro drag elements. So the first step is to look at the aeroelastic stability. For this purpose, we use Hawkstep 2. In the animation here, you can see an animation of the lowest damp edgewise mode, the first backward whirling mode. And essentially we check how frequencies are placed relative to each other, and that overall we see a positive aeroelastic damping of the full system, which we do. Next, we simulated the turbine according to a DTU interpretation of the IEA standard. And so far we've limited this analysis to DLC 1.2 and 1.3 that we use for verifying the design limits. Here we see some examples of these loads that come out for both the bottom fixed and floating configurations. We see in the first column blade roof flap, and in the second column the tower bottom fore aft moment. And one notable thing perhaps is that for the floating platform, the tower bottom moments are quite high, and there's certainly work needed to address this issue, hopefully through control, but this is under active investigation. So then I'll turn over the word to Will.
Thanks, Frederick. I'm Will Collier from the Bladed team at DNV, and DNV's contribution to this work was to lead the code comparison study between the 4 tools that you can see on the screen: Bladed, Hawk 2, OpenFast, and QBlade. The code comparison is focused on the offshore monopile case, so we haven't done a detailed code comparison for the floater, just for the fixed bottom case. So why are we interested in code comparison? There's a few reasons listed here that we want to have a look at the whether the tools give the same predictions, so we can understand how much uncertainty is coming from the Aeroelastic tool differences for very large turbines. And we also wanted to intentionally expose differences between the tools, so we can identify areas where we need to do further study. Thirdly, we want to provide Aeroelastic models to the community as a basis for further research. And the last point, we also are providing a baseline set of results in a publication and on the GitHub, so other tools can use that as a baseline to compare to. So we've done various different comparison types, that just showing a few samples here. So at the top left, we've done comparisons of masses and frequencies of various parts of the turbine. You can see a sample of the blade frequencies there. The next one, steady state analyses. So we've run steady wind cases, and we're looking at what's the steady state operation conditions and loads and deformations against wind speed. The bottom left, we've looked at azimuthal variation. So how do the loads and deflections and angle of attack and so on vary as the rotor rotates, as the loads change on each blade. The next one, linear stability analysis. So looking at the turbine coupled modes, so build a linearized model and then calculate the turbine modes, the frequency and the damping. And the last one, we've also run the models in all the codes in time domain and then compared in that case as well. So I'm just going to look at two different cases just to give a kind of flavor of the differences. So this is some of the steady state results. So there's a bit to digest here, but I mean, the main message is that the lines mostly overlap. So we get a good agreement in the steady state. So the top plots are kind of the operating condition, main parameters, the rotor speed, pitch angle, electrical power, and then rotor torque and thrust and the tip speed ratio, all agreeing well. And then some of the basic things like the blade deformations also agreeing well. Here's the torsion, for example, at 80% of the blade span-wise position, agreeing well between the codes. So this is a good sign that the basic parameters of the models are well aligned for this simple case. In the dynamic cases, I'm not going to show them all, just going to show the time domain. The general story in the dynamic cases is that we see slightly larger differences. So this is looking at some time domain statistics for the blade root loads. I'll just have a look at the coordinate system here. The MX is the edgewise and the MY is the blade root flapwise loading. So here's the solid lines, the mean, standard deviation and maximum, and then minimum down there for the blade root edgewise load, and then something similar with a familiar shape for the blade root flapwise load. So generally seeing excellent agreement on the means, and then slightly some differences with the minima and maxima. And then just further down for the damage equivalent loads, this is in this case, so I'll start on the right. For the flapwise, we see a good agreement between all four codes, so evaluating the damage equivalent load in isolation at each wind speed. And in this case, in the edgewise case, we see Hawk 2 giving some slightly higher damage equivalent load at high wind speeds compared to the others. So this is one example of an area where we need to investigate more to understand, does this come from some extra physics captured in Hawk 2, or does it come from some difference in the inputs, or we need to do a bit of further work in this case and some others to understand where the sources of difference are. Generally, the alignment is very good. So yeah, the study conclusions, the steady state's very well aligned. The dynamic cases generally agree well, but there are some differences that we need to look into a bit more across the more complicated cases like the azimuthal variation, the stability analysis, and the time domain. All of these results were presented at the Talk from Wind conference, so you can go and look up this paper. If you're desperate for a preprint, you can feel free to get in touch with me, and there's an email address there if you want to get hold of a preprint in the meanwhile, but I think that will be released shortly.
Okay, thanks, Will. Then I just need to grab control again. So besides the medium fidelity modeling that has certainly been the main focus of our work with the turbine so far, we had another paper presented at the Talk conference where we also introduce high fidelity aerodynamic modeling into the mix. And in this paper, we outline we describe a comparison between high fidelity aerodynamic modeling coupled to Hawk 2 in the form of our Ellipsis 3D CFD solver, coupled to the static Hawk 2 solver, and then comparing that to the medium fidelity codes that we typically use in a design context, ranging from BEM to a near-wake vortex cylinder model that captures a bit more physics than a classical BEM code, and look at how well these different fidelities compare. Again, these papers are about to be released through IOP, but not yet fully available, but they will be shortly. Now, turning to some wrap-up availability. The report I described was available. If you want to dive into all the data, you need to go to GitHub, where at this address shown here, you can download the data files in the form of a Wind.io definition of the wind turbine, as well as Aeroelastic code definitions of the turbine in Hawk2 OpenFast and QBlade, as well as wisdom inputs to run analysis of the turbine. There's also a bladed model, and this is distributed directly by DNV using through their bladed portal. Then, in terms of what happens next, we of course expect there to be questions and feedback on the design. Please use GitHub to report these issues. We prefer that over email because then everyone can see it. We try to maintain an FAQ, so please also consult that before you ask any questions. And we certainly already have some issues that need to be addressed, need to update the design. This will also happen in this repository. So what's next with the design? We already had some feedback on the tower, the floating tower. It needs another iteration in design. This will be addressed. We also had some feedback on this monopile diameter that I'm not sure we're going to change, but at least it's we noted and acknowledge that this is currently a barrier that is not realistic. In terms of high fidelity modeling, we've also had some feedback, and there will be some work in high fidelity model definition, both with respect to CFD as well as full 3D finite element models that are under development but haven't yet been released. The 3D CFD meshes that were used in the study we presented at Torque will also be made available once we have updated the root design of the blade that right now results in some unwanted non-smooth shapes at the very inner part of the blade. In the Task 55 group, we are also organizing a task on designing a wind farm using these 22 megawatt turbine. This will be a bottom-fixed wind farm that's under work, and if you have interest in this, please you can join the task if you're a member country, or encourage your country representatives to join the task. This will also be discussed publicly in more detail once available. There will also be new reference land-based turbines released in Task 55, and we will, of course, update you on this. We have a LinkedIn profile that we encourage you to follow, where we will update on all these matters. Right. So that ends the presentation. So next we can perhaps address some questions if there are any. I just need to.
Yep, I can. I can start reading some of them. The first one is about the floating tower. And it is we did receive feedback that it's too low. The background there is that the floating tower is identical to the fixed bottom tower, and that's not realistic. So we will need to work on a redesign, and we will do that at NREL, at least at NREL, maybe more in more organizations, but at NREL we will use WISE, our floating design framework, whose development is led by Dan Zalkan here. Another question is whether the 22 megawatt is floating. Yes, it is. It can be floating, or it can be, or it is fixed bottom. So it's it comes with the two substructures. Then I think there is a question for you about the natural frequencies of the turbine. Is there any, I'll read it. Is there any consideration of the coupled tower eigenfrequency and 3P separation in the optimization process?
I think we tried to keep no, we didn't. I think we just used the same floating tower, and that natural frequency drifts up towards the 3P, and I think that it's a little bit too close to 3P for our liking. And we've gotten a lot of very strong feedback about whether we should use a soft stiff or a stiff platform, and there's still not a lot of consensus. So we have a soft stiff platform here. I saw another question in the chat about if we have any resonance avoidance. No, we haven't enabled that, but I think both the DTU and the Rosco controllers have those in there. So I think that if we were to design a floating platform from scratch, we'd want to enable those as well and make sure they're active, because that's important.
Frederick, there is thank you, Dan. There is a question for you from Haris. For these such huge rotors, do you think the aerodynamics predicted by the low fidelity codes is accurate enough? Does the compressibility plays role for these rotors? Can we model these rotors in CFD?
Yeah, so a couple of questions. In our comparison so far between the static response, aeroelastic response between high fidelity CFD coupled to Hawk 2 and versus the medium fidelity codes, we actually see very good agreement. We use airfoil data based on incompressible CFD, 2D CFD. Compressible effects could be at play for certain operating conditions where you will see locally very isolated and perhaps to the leading edges where you would see a transonic flow that could have an influence. So that's certainly a topic that we should look further into. I also see a question about CAD files for the blade from Esteban. Yes, there will be CAD files available that will be released. It probably will be in a separate repository, but we will release it once we have smoothened up the geometry from what we have now.
In the chat, there is also a question about the scope of Task 55, and the scope is to design relevant reference wind energy systems. That means both wind turbines and wind farms, and both land-based and offshore. They can be fixed bottom and floating. There is, I will post in a second the link to the IEA webpage where the Task 55 is described. Task 55 started in October 2023, and so we are in the first year, and it will run for 3 more years.
I see a question on the carbon fiber composites. Was there any study analysis on possible lamination stacking sequence? I suppose by this is meant whether this was optimized. The stacking sequence is kept constant, so we choose you could say a stacking sequence with a sequence of different materials in the different parts of the blade. They are kept constant, but we optimize the thickness of each of these materials in the different areas of the blade. So spar cap, leading edge reinforcement, trailing edge reinforcement. But others are kept constant. So for example, the skin laminates are kept constant during the optimization. But otherwise, it's, you could say, a fairly low fidelity structural representation.
And the same holds true for bolts and bolt size. I don't think we went down that path. We have some simple analytical laws in Wisdom that we could use for blade root bolts, but then there are bolts all over the place, right? And we did not size them. That would be one level up in terms of fidelity. Thank you, Kevin, for the question.
For dynamic modeling, how was blade torsion modeled? This is done slightly differently between the different aeroelastic codes, but essentially it's a beam model that for all our cases could take into account the fully populated stiffness matrix. computed with cross-sectional finite element tools, in our case, BCAS. This is handled both in bladed open-fast and Hawk 2 and Q-blade in fairly similar manners.
Dan, a question for you. Was the floater redesigned or simply enlarged?
It was redesigned, but the outcome, looks like it was enlarged, so it gives us some confidence.
One question for you, Frederick, from Francesco Papi. How were the blade geometries designed for CFD? Did you start from Wind.io or from anywhere else?
Yeah, so we have an in-house Python-based tool that we use to loft the blade. So we take the Wind.io definition of the planform, the base airfoils, and interpolating these to loft the blade. And then, of course, for CFD, we need to make a watertight surface with a given topology, which is handled by this in-house Python tool. This is available, and we can certainly also, when we release the CFD-ready meshes, make the script available to run this tool called PGL. If you want to, for example, change resolution, we will probably release it as also as plot3D files. This is at least something we use heavily. People can certainly also contribute an open format for it if they wish. We could probably also export it to some VTK format if needed.
Will, one question for you. Did you compare the coupled structural frequencies of the tower and the floater across different codes?
So certainly for the fixed bottom case, yeah, we've had a look at that. So we looked at the uncoupled tower frequencies and did a comparison, and we've also done comparisons of the turbine coupled frequencies. We presented in the paper the coupled frequencies are compared with a rigid tower, so we could focus on the rotor modes. But we have also done some tests with the tower flexibility included. That's not presented in the paper. I don't know if there's anything else for the floating side that you've that you did, Pietro or Frederick.
I think, yeah, on the floating side, we would need to that's a national extension of the work to keep going on in terms of detailed code-to-code comparisons. I think we really focused on the rotor, and then we started doing some comparisons, including the tower and the monopile. But for the floating side, that's an extension that we haven't got to yet.
Pietro, there's a question for you. OpenFast. I assume the code-to-code comparison used beamdyne. Would the results drastically change using Elastodyne? Yeah,
they would, and we don't. We tend not to trust Elastodyne at this scale. You saw some plots from Frederick in terms of blade torsion up to 6 degrees. That's directly impacting the angles of attack. So you are correct, Jesse. We used beamdyne, and we're not planning to use Elastodyne for detailed rotor studies. Maybe I'll just say that we used Elastodyne during the floater optimization, just for sake of speed. Beamdyne is still very slow, and we're working to speed it up.
Is there any control algorithm used for load reduction? Yeah, I suppose Dan on the Roscoe side, you could maybe answer that.
The main one for load reduction is this peak shaving that was used in the rotor design, but we didn't, by default enable any individual pitch control or dampers in the controller.
And I suppose in the peak shaving, it's simply a minimum pitch ramp that you prescribe according to the mean wind speed window, you could say. Not any sort of with any sensors or anything like this on loads.
Yep, that's right.
Same for the Hawk 2 controller. It's also a minimum pitch ramp that we impose. Is fatigue taken into account in the design of the monopile?
No, it's yeah, I answered it somewhere else, but no, we did not include fatigue in the design. That's a clear limitation of our approaches, and that would be a nice extension of this work. There is a question about the timeline for the land-based reference wind turbines, and it's a little bit unclear. We need they were planned for next year. But we need some projects in the organizations participating in Task 55, and these projects are not exactly clear right now. We have quite a few starting points, though, and so we could, yeah, we've been pushing the can down the road, kicking the can down the road at this point. It might be later next year. There was a question. There is also a question about stiff versus soft stiff for the tower, and again, for the floater, we might need to rethink the tower a little bit. But it was not. We did not think that it was realistic to design a stiff tower at this scale. The tower masses were simply, well, I would say outrageous. So. Right now, it's a soft stiff design.
What else do we have?
There's a few questions about the mooring system. We use kind of the same architecture as the 15 megawatt. It's the 3-line catenary mooring system. Yeah, that 400 millimeter chain diameter, I don't think is volume specific. I've got it going up from 185 millimeters at the 15 megawatt to 225 for this 22 megawatt machine. But we already got some feedback that those line diameters are, probably don't exist. So I think that, yeah, looking into alternative mooring configurations, and we did not include the fatigue there. So yeah, that's an interesting design challenge that we left out of the scope here.
What about Aeroelastic code comparison part, and which dynamic stall models were used? So for bladed, Hawk 2, and OpenFast, they all use flavors of the Leishman dynamic stall, and Keyblade is using an OI dynamic stall model in this case. So some slight differences coming in there, either with the theory used or slight implementation differences between the codes, but at least 3 of them are using the same basic theory.
There is also a question about the tip speed, the maximum tip speed of 105 meters per second. Maybe one thing we didn't say explicitly is that before embarking into the design process, we ran a survey that was sent out to the community, and there was one question explicit on the maximum tip speed that 105 would return. It was the most voted selection, and there was industrial feedback on that as well.
There's a quick one here about the cone angle. Cone angle is 4 degrees with a tilt angle of 6 degrees also. Which
yeah, there is a question about the OrcaFlex model, and yes, Orkina has developed a model for the 22 megawatt. The link is available. I think the model is publicly available on the Orkina website, and there is a link in the README on GitHub. Whereas we don't know, we have not run a comparison to the Mingyang 22 megawatt that was announced last year. We don't know how the two models compare. Frederick, one question for you on the leading edge protection.
Where did that one? Can you?
Oh,
yeah, was there a leading edge protection system included? No, there isn't. This could of course have some impact on I suppose mostly the aerodynamic properties of the airfoils, but no, was not considered. Except that of course with 105 meter tip speed, we are certainly expecting advancement in leading edge protection systems compared to what's currently done in the market, I think. So definitely you could say on the challenging side of things.
Daniel Rybnitsky, I'll take your question. Oh, definitely. Yeah. So the dynamic stall models have been giving us a lot of headaches, at least on the been giving me a lot of headaches in OpenFast. And so right now the OpenFast model on the repository has the OpenFast has all the different options, so the different implementation of the Beddoes-Leishman model, and so yeah, I would start from that selection and expand from there. But the answer is yes, absolutely. Then a question for you on the control, whether the controller uses tower top velocity feedback, whether its purpose is to reduce the ultimate load or stabilize the floating platform.
Yeah, it effectively does both. It's mainly to stabilize the platform, but in doing that, ultimate loads are reduced.
Synthetic mooring lines, have you tried that? Are we planning to?
We haven't tried it, but yeah, it's definitely on our radar. And there's another IEA task, I think it's 49, that does floating wind farms, and they have some pretty nice mooring configuration work there.
Yeah, at the recent Task 55 meeting, we had a session with this task. There's of course a big overlap between the two tasks. They're currently primarily using the 15 megawatt, but we were discussing whether what were the perspectives for a 22 megawatt wind farm. This is still not decided yet, but definitely something where we need to work together across the tasks.
I'm trying to filter out some questions in the last couple of minutes. I don't know, Dan, have we considered extreme wave load conditions in the design of the monopile? Well, that's actually a question for me. No, I don't think we have.
Yeah, then there's a question about CAD files for the blades with various loading. No, we're not planning to release the blade in, you could say, loaded conditions. So if you don't have an elastic model, suppose we could do it maybe more on a need basis. But yeah, we could maybe talk offline about it. But no, right now it's not in the scope to have that you could say officially released at least. What else do we have?
One question, Iñaki, I think I partially answered this already, but yeah, we did not. I don't think a stiff configuration will be viable, at least for now, unless we maybe change the hub height. But even then, so we were not able to imagine a stiff configuration for now. For the floating wind right now, that one question from Irati on the tower strikes. Yeah, so we don't have tower strikes in the design during the Aeroelastic simulations. Right now, the tower is designed to have a 10 meter. Well, there in one of the slides there is the distribution of the tower diameters, and it decreases when going up. But yeah, certainly that might change when we redesign the tower for the floating configuration. But even then, we will make sure that we don't have tower strikes.
Okay. Should we wrap up? Do we have any more questions to answer? Otherwise, I will encourage you to reach out if you have any other burning questions or other things you identify as you start looking closer at the turbine. Please use the GitHub issue tracking system, and we will address all those questions. And when you start modeling it, please also give us feedback. If you publish on the 22, we would also appreciate, first of all, of course, that you cite the turbine, and please also let us know that you are publishing on this and using it. If you're in big projects, it's also great that these types of reference systems can be used in big national projects. That would also be great to hear about. Right.
The recording will be made available on YouTube, and we will share the link on LinkedIn on the page of Task 55 as soon as it becomes available.
Great. Okay, I think we are ready to wrap this webinar up, and thanks very much for attending and all the great questions, and we hope that this new reference turbine will be useful in your work or research. And thank you to my co-presenters, Pietro, Dan, and Will. And yeah, thank you very much.